Now, one last thing I want to finish with. We have these 5 schemes. And accuracy is something you just prescribe by pick your accuracy you want, then it's going to prescribe what you do here with your delta t and delta x's. And you can put it in your computer, iterate. Now, what do you like about some schemes? Well, I like how simple that looks. I don't like that, right? I can't use it. So the one I really want to use, I can't use. Well, leapfrog, at least I got a region of stability. Leapfrog 2, 4, I have the region of stability. Lambda's 1. You know, the bigger it is, the bigger time step I can take, the faster my code's going to run. Lax-Windruff is 45. Here's this one here. Wow, that looks... who wants to do that? Nobody. It's going to cost your code a lot. Slow it down. But boy, I love that. Is there any way to sort of gain the power of this without paying the price? Okay? So there is some methods that have been developed to try to take advantage of this fact. Okay? Called McCormick schemes or predictor correctors. Okay, so how do these schemes work? Well, the big problem in an implicit scheme like this is you say, I have my future, it's what it is now, plus the future. And here's what the problem all lies. You know what the future is. You're going to pay a high price to try to get it. So how about instead, I try to predict the future and use my predicted future point in this scheme. Okay? So I'm not going to actually use the real future. I'm going to use something that looks sort of like the future. I know. This is where the Terminator movies came from playing with these schemes. Okay? Predictor corrector. That's T1. They go out, and then T2 has to fix it, and then T3, and then there's T4. Everything keeps changing, right? Have you guys watched all of them? No? Well, I have. Okay. So let's think about this. So first of all, let's predict the future. And I want to predict the future with the simplest scheme possible. Let's go back for that leapfrog. And here's what I'm going to do. My future will be what it is now, plus a little bit of something. And I think I'm missing a 2 there in the notes. I take my current point, add something to it, I get a prediction of the future. Now, notice, if I were to use this this forward Euler as a stepping algorithm for the future over and over again, right? If I were to put it in an iteration scheme, it would blow up. I'm only using it for 1 delta t step. Schemes don't blow up in 1 delta t. It takes them a while to blow up. So I'm just using it for 1 delta t. But what I have now is a quantity, okay, that is approximating my future. This is my prediction for the future. And now I can say, well, since I have a prediction for the future, why don't I use that prediction in the future in the backward Euler? My future is what it is now plus the future. And instead of having to compute the future, I'll use my predicted future here. Okay? So now I can just get my solution out, which is in fact, what I'm going to do here is do this. So what I do is I say, okay, there's the 1/2 here, which is this is my derivative that was creating the right-hand side problems. So I'm using my predicted future points for calculating that derivative. Not my current points, but my future points. And then what I do here is say my future, I'm not even going to use what it is now. I'm going to say my future is not what it is now plus a correction. My future is sort of an average of what it is now plus what I'm predicting it to be It's, in other words, what it is now plus what my future was predicted to be divided by 2, so it's an average. So I predicted this future point, I averaged the value, plus I added the correction. And so what you do is you set this thing up in a loop. And what you've actually done with this whole scheme is you've set up a system that tries to do what? It tries to take advantage of the implicit scheme, but it's still explicit now. Okay? So it's two-stage iteration, trying to make use of that really nice stability property.
Would it work to not use u sub n at point m plus the lambda over 2? If you didn't have that extra, when you're averaging the first term, and that's just the flavor of it, and you didn't do that, would
Yeah, you
work?
could still do this, for instance, but this seems to be, this is the more standard method, is to take the average of the 2. Since you already sort of have a prediction to the future, you just say, well, okay, I think it's here, let's just average it. Now, let me make a comment about this. So this is still using sort of second-order accurate methods in space and time. And if you wanted to implement this scheme as a stepping scheme, you could do that. And in fact, you can make it more accurate by using more points and so forth. And you already have access to this. ODE 113, which you've used in homework 2. What is it? If you look at ODE 113 and what it does, it's a variable order accuracy predictor corrector scheme. Okay? It tries to take care of this issue here, which is if you've got something that will blow up on you, the predictor corrector tries to take care of it. And by the way, it uses variable order accuracy, so it just decides, look, I want to try to take as big a delta t steps as I can take, right? So it has this constraint on the CFL condition. It's just trying to take as big a step as it can. And sometimes, just as illustrated here with the leapfrog, in the leapfrog, notice that if I want to get better, you know, for prescribed accuracy, it's probably better that I use a higher order scheme versus just cranking down my delta x and then cranking down the delta t correspondingly. Okay? So here, it makes a lot more sense to use higher order schemes. And so 113 uses higher order schemes. Now, final comments.
I'm sorry.
Yeah.
ODE 113 is this higher order scheme, or it's doing this predictor corrector with a higher order scheme?
With higher order spatial schemes, yeah. Let's talk about that delta t over delta x. That delta t over delta x comes up only because we have ut equals ux. In other words, one derivative in time, one derivative in space. Things get worse. If I had things like this, ut equals uxx, and we'll talk about this next time in class, I put a squared there. How does that affect things? Well, let me tell you how it affects things. If you have a constant lambda, CFL, that will make this thing work. If I want to double my accuracy spatially, all of a sudden I get a factor of 4 underneath there. To keep the same number, I got to take this down by a factor of 4. Okay? So you've done 4 times as much work here and 4 times as much work there, which is 16 times. You load 16 tons. What? No? You guys don't know that song? You guys don't know 16 tons? Okay, that's like 16 tons. Which version? I don't know. Johnny Cash's. Let's take that one. Yeah, look that up after class. It's going to be homework now. Because obviously I have to make it a homework if you guys aren't learned. All right, 16 tons. Well, 16 times slower code. Right? This is the cost to use. So this is why the CFL becomes so important. It tells you about time and space and how they relate. Double. You want to double your spatial accuracy? Be ready to pay for it. Okay? The higher the derivative, the smaller step you got to take. That's called numerical stiffness, essentially. So if you have a 10th derivative here, what do you think is going to happen there? Delta x to the 10. See how you can get yourself in trouble real quick? Okay, so anyway, these are things to keep in mind on the stability front. Remember, everything's just an iteration scheme, but you need that iteration scheme not to blow up on you. That's the imperative. Okay? And if it does, it'll tell you, as we'll see in class. That's it for today.